Swayam Prabha. Digital India. Educated India.
Welcome to lecture 30 on time series modeling and forecasting. In one of the earlier lecture, in lecture 6, we discussed different methods for the determination of seasonal indices. In this lecture, we will consider handling of seasonal variations using the Box-Jenkins approach. In particular, we will consider different seasonal models, seasonal autoregressive integrated moving average models. Using seasonal autoregressive integrated moving average models, you can model different kind of seasonalities present in the data. The non-stationary behavior of the time series may be due to the presence of trend component, it may be due to the presence of unit roots, and along with the other reasons, one of the possible reason is the presence of seasonal behavior. And actually, when seasonality is present, then mean of the observations is not consistent. The mean of the observations evolves according to some cyclical pattern. So, the process is not mean stationary. Then the question is how to handle such kind of non-stationarity or how to model such kind of seasonal non-stationarity. Now, here is an example. Suppose you have data on monthly rainfall in Delhi, then naturally the rainfall is not constant and it varies by month or by quarters. At least expected rainfall varies by months or quarters. Then for the same month in different years, what we expect? We expect a constant expected value, provided there is no trend or trend has been already eliminated from the data. So, if there is no trend in the data, then you expect that the same month, say for example, if you take August, then the August of each and every year, of course, it may not have the same rainfall, but you expect or expected rainfall of August for each and every year will be the same. Then in lecture 6, we have discussed different methods for obtaining seasonal indices, and some of the methods are the simple averages method, ratio to trend method, method of link relatives, and these methods are unable to provide a link between current observation with the past observations due to seasonality. So, basically all these methods try to extract the seasonal component from the variation in the time series. But how the seasonality has evolved with a link between current observation and the past observations due to seasonality, that particular point these methods do not explore, or with these methods we do not get some idea of such kind of link. Now, we consider the concept of seasonality and different types of seasonality. So, suppose y_t is a time series and we assume that the time series does not have any trend. Then we say that y_t is seasonal with period of seasonality s if expected value of y_t is equal to expected value of y_t plus s for all t. So, expected value of y_t varies in a cyclical pattern. For instance, if your time series has monthly seasonality, then s is equal to 12, and if your time series has quarterly seasonality, then s is equal to 4. So, usually s is fixed number of observations making a seasonal cycle. So, normally we assume that s is fixed. Now, let us consider an example. We consider series of daily data on people visiting a supermarket. So, this time series may have a seasonal pattern, and the period of seasonality may be length of the month. Usually, we expect that the number of people visiting the supermarket increases during the first week of each month, because most of the people get salary on first of each month. So, they prefer to do shopping during the first week of each month. So, you observe some kind of seasonal pattern, and then the period of seasonal pattern is length of the month. So, s is approximately equal to 30. Of course, it may vary from month to month, because some months have 30 days, some months have 31 days, and even February has 28 or 29 days. So, this period may vary, but here we are assuming that s is fixed, and we also assume that except for its seasonal effect, series is stationary and s is fixed. Let us write y_t equal to STS plus eta t, where STS is the seasonal effect of period s at time t, and eta t is stationary part after eliminating the seasonal effect. And we assume that expected value of eta t is mu. Then we take expectation of both sides of equation 1. So, you get expectation of y_t equal to expectation of STS plus expectation of eta t, and we have assumed that expectation of eta t is mu. So, you get mu here. Now, we consider different types of seasonality. STS. Now, the case 1 is seasonality is a deterministic process. So, suppose seasonality is a constant function for the same month in different years. So, STS is equal to ST plus Ks for all k equal to plus minus 1 plus minus 2 and so on. So, after a period of S, the seasonality repeats itself. For example, suppose STS follows a sinusoidal function, say sine function or cosine function, and such kind of sinusoidal functions occur in climate series because of Earth's rotation. So, in that case, you observe this kind of phenomena. After a certain period, the series repeats itself. Of course, usually representing such seasonality using sinusoidal functions is inefficient. So, normally we do not use sinusoidal functions to represent the seasonality. Suppose for example, you have monthly data, then you may introduce 11 dummy variables, one for each month of the year. So, this is one possibility. You introduce 11 dummy variables, one dummy variable for each month, and then you proceed. The second case is seasonality evolves over time as a stationary process. So, your seasonality factor is STS, and this is a stationary process oscillating around some mean, say mu s. So, STS is equal to mu s plus Vt, expected value of Vt is equal to 0. Mu s is deterministic effect of seasonality depending on s, and Vt is a stationary process and introduces variability in STS. So, this STS has two parts. One is the deterministic effect of seasonality, and this part depends upon S. And then it has second part Vt, which is a stationary process, and because of this part we get variability in STS, and we also assume that expected value of Vt is equal to 0. Now, we consider case 3. In case 3, the seasonality changes over time with no fixed average value. So, seasonality is a non-stationary process. So, the seasonality may follow any non-stationary process, and suppose STS evolves according to a random walk. You know, random walk is a non-stationary process. So, we take STS equal to ST minus S plus Vt, and notice that in this random walk the lag of this term is not 1 like usual random walk, it is t minus s, where s is the period of seasonality. Now, we define seasonal difference operator of period s. Delta s is equal to 1 minus B s, where B is the backward shift operator. Then delta s y t is equal to 1 minus B s y t. So, this is equal to y t minus s. So, the difference between the current value of y, say y t, and s period lagged value of y t minus s. Then applying the operator delta s to equation 1, this was equation 1, y t equal to S T s plus eta t, we get delta s y t is equal to delta s S T s plus delta s eta t. Now, delta s S T s is equal to, if you look at this equation, then delta s S T s is equal to V t. So, we obtain a stationary process. Actually, if you take this difference, then we obtain a stationary process. Delta s S T s is equal to V t, this is stationary, and delta s eta t is also stationary. So, in all the three cases, the seasonal series can be changed into a stationary series by applying seasonal difference. So, let us consider the first case. STS is deterministic. So, STS is equal to ST plus K S S. Now, delta S S T S is equal to S T S minus S T minus S S, means delta S S T S is equal to S T S minus S T minus S S. So, if you take k equal to minus 1, then S T S is equal to S T minus S S. So, this is equal to 0. So, delta S y t is equal to delta S eta, which is a stationary process. Then the second case is S T S is a stationary process. S T S is equal to mu s plus V t. Again, delta S S T S is equal to delta S V t, because delta S mu s is equal to 0. So, delta S y t is equal to delta S V t plus delta S eta t, which is equal to V t plus eta t minus V t minus S plus eta t minus S. Now, this is a stationary process. Then we consider case 3. S T S is non-stationary process. It follows a random walk like this. S T S is equal to S t minus S S plus V t. Again, delta S y t is equal to V t plus delta S eta t. Again, this is a stationary process. V t is a stationary process, and since eta t is a stationary process, delta S eta t is also a stationary process. So, in all the three cases, if you take the seasonal difference delta S, then ultimately you get a stationary process. So, you can remove the non-stationarity because of seasonality by taking a difference delta S, a seasonal difference delta S. Under fairly general conditions and for processes with deterministic as well as stochastic seasonality structure, this seasonal difference delta S transforms a seasonal process into a stationary one. Now, this is an important observation, and this important observation helps you in developing seasonal models. So, now we consider seasonal autoregressive integrated moving average models or SARIMA models. The basis behind SARIMA models is we can convert non-stationary series into stationary ones by taking regular differences. This is what we do in integrated processes. If your time series is non-stationary, then you in integrated processes you take some regular differences and then it reduces to a stationary time series. And then we can eliminate seasonality by taking seasonal differences. This is what we have all observed earlier. The seasonality can be eliminated by taking seasonal differences. So, we can convert a non-stationary series with seasonality into a stationary one by using the transformation Z t equal to 1 minus B s to the power capital D, 1 minus b to the power small d y t. So, suppose you have a non-stationary series and it has seasonality also. Then you can convert or you can reduce that series into a stationary series by using this transformation Z t equal to 1 minus B s to the power capital D. This part removes the non-stationarity because of seasonality, and then 1 minus b to the power d. This is your regular difference of order small d, which removes the normal non-stationary behavior of the time series y t. So, capital D is the number of seasonal differences. Usually, we take capital D equal to 1 or 0. Small d is the number of regular differences, and usually we do not go beyond 3 differences. Then we model the regular and seasonal dependence separately and then construct the model incorporating both multiplicatively. So, you have phi p b s small phi p b 1 minus b s t 1 minus b small d y t equal to theta q b s theta q b u t. So, basically what you have done, you have applied these two differences just to remove the usual non-stationarity in the series and seasonality in the series. So, after that your series becomes stationary. This 1 minus b s to the power capital D, 1 minus b to the power small d y t is a stationary series. And suppose this stationary series follows Arma PQ process in the usual backward shift operator and Arma, again it follows Arma process with order capital P of autoregressive term and order capital Q of moving average term because of seasonality. Or you can say phi p b s is equal to 1 minus phi 1 b s 1 minus phi p b to the power s to the power p is the seasonal autoregressive operator of order p. Small phi p is the regular autoregressive operator of order small p. Similarly, theta capital Q b s is the seasonal moving average operator of order capital Q, and small theta q b is the regular moving average operator of order Q. U t is of course the white noise process. Then we write the model 5 as autoregressive integrated moving average model of order p d q, and p in this part denotes the seasonal part into capital P, capital D, capital Q S process. So, here this is small p, small d, small q, these are the orders of usual autoregressive moving average and integrated part, and then here capital P, capital Q and capital D denotes. So, capital P is the order of seasonal autoregressive part, capital Q is the order of seasonal moving average part, and then you are taking capital D seasonal differences. So, this model provides a good representation of many seasonal series. So, this is the general seasonal autoregressive integrated moving average model. Now, for further motivation, we consider the time series of monthly data on R years. So, here you have 12 months and then you have R years, and then your observations are y 1, y 2, so on y 12, y 13, y 14, so on y 24 and so on, y 12 r minus 1 plus 1, y 12 r minus 1 plus 2, so on y 12 r. So, this is the time series for the month of January. This time series is for the month of February and so on. This time series is for the month of December. Now, each column may be considered as a realization of a time series generated by the same process, or you can say between seasonal dependence. Then the time series between different months of a year also have dependence, means within seasonal dependence. So, row wise you will get within seasonal dependence, and column wise you get between seasonal dependence. Now, each column may be considered as a realization of a time series generated by the same process RMA capital P capital Q, say phi P B 12 y t equal to theta q B 12 u t. Means if you look at any column, then the observation before y 13 is y 1. Then here you will get 25th observation. So, the lag between two observations is of period 12. So, that is why we have taken B 12 here, and this is the between season model. Then for incorporating the dependence between series at different months, we assume that U t follows ARMA P q process. Here you have capital U t, and this U t follows ARMA P q process. So, phi p b u t equal to theta q b small u t, where small u t is a white noise process. Now, this models dependence within 12 sequences u j plus 12 t. Then your final model is phi p b 12 small phi p b y t equal to theta q B 12 phi p b u t, or theta q B 12 theta small q b u t. Then allowing for differencing, we get the general seasonal ARIMA process. Here we have not taken any difference, but if you have non-stationarity also, then we allow for differencing, and then we get seasonal ARIMA processes. Now, we obtain autocorrelation function for these processes. Now, for the process with ACVF gamma k, the autocovariance generating function is defined as gamma b equal to summation over k gamma k b to the power k. Then the autocovariance generating function of a general linear process is, suppose you take this general linear process y t equal to 1 plus summation over I equal to 1 to infinity theta I b to the power I u t or theta b u t, the autocovariance generating function is gamma b equal to sigma square u theta b inverse into theta b. So, this is a simple procedure for obtaining the autocovariance generating function. Then x t equal to 1 minus b to the power d 1 minus b s to the power d y t follows a stationary process. So, phi p b s small phi p b x t equal to theta q b theta capital Q b s u t. This is the process for x t. And then for obtaining the ACF of this process, let us consider the following two processes, phi p b x t equal to theta q b u t and capital phi p b s z t equal to theta q b s v t. Then both of these are stationary processes. And then we can write these as general linear processes. So, we write 7 as x t equal to psi b u t and we write 8 as z t equal to capital psi b s v t. So, we have written both of these processes as general linear processes, and this is possible because both of these processes are stationary processes, where small psi b is summation over j psi j b to the power j and capital psi b s is equal to summation over j capital psi j b to the power s j. So, hence we can write this equation 6 in the form of a general linear process as x t equal to psi b capital psi b s u t. Now, you know the result that if you have y t equal to say psi b u t, then its autocovariance generating function is psi b inverse, and the ith autocovariance is given by the coefficient of b to the power I in this autocovariance generating function. So, now we are going to use this result. So, suppose C I is the autocovariance of ARMA PQ process 7 or 9 and R I is the autocorrelation of this ARMA PQ process. Then C I is the coefficient of b to the power I in psi b inverse. Similarly, if capital C S j is the autocovariance and capital R S j is the autocorrelation of seasonal ARMA PQ processes 8 or 10, then C S j is the coefficient of b to the power S j in capital psi b to the power S capital psi b to the power minus S. Now, if gamma k and rho k are the autocovariance and autocorrelation of the process 6 or 11, then gamma k is the coefficient of b to the power k in psi b inverse capital psi b s capital psi b s inverse. So, your problem is to find the coefficient of b to the power k in this product. So, gamma k is equal to C naught C to the k plus summation I equal to 1 to infinity. You have CSI. CSI is the coefficient of B to the power Si in capital psi Bs, capital psi Bs inverse into CSI minus k plus CSI plus k. So, this expression gives you gamma k. And then if you take capital C naught, small c naught common, then inside you get R k here plus summation I equal to 1 to infinity, you get R S I here, then you get small r S I minus k here, and then R S I plus k here. So, this is the expression for gamma k. K equal to 0, you have gamma 0 equal to C capital C 0 small c 0 into 1 plus 2 times summation I equal to 1 to infinity capital R S I into small r S I. So, using equation 12 and 13, you can easily obtain the kth autocorrelation coefficient rho k. We simply divide gamma k given in equation 12 by gamma 0 given in equation 13. So, you get this expression for rho k. So, you get this expression for rho k as a function of autocorrelations of the ARMA process and the autocorrelations of the seasonal ARMA process. For example, suppose S is equal to 12, then you know that for the stationary ARMA process, for large j, R j is approximately equal to 0. Say for j greater than or equal to 8, R j is approximately equal to 0. So, we neglect it. Then we consider the denominator of 14. In the denominator, this capital R S I is non-zero for I equal to 12. Before that, capital R S I will be equal to 0, but small r S I is negligible for j greater than or equal to 8. So, this denominator is approximately equal to 1. Then the ACF is in small lags, say for j equal to 1, 2, so on up to say 6. Rho k is approximately equal to R k, because this part vanishes. Means either this term is 0 or the first value for which this term may be non-zero is I equal to 12, but for that value these two are 0. So, rho k is approximately equal to R k. Now, in seasonal lags, rho 12 k is approximately equal to, for that this part is approximately equal to 0, you get R 12 k into R 0 plus R 24 from here, plus R 24 k, R 12 k plus R 36 k, and then this is approximately equal to 0, R 24, R 12 k is approximately equal to 0, R 36 k is approximately equal to 0. So, approximately it is equal to R 12 k. Rho 12 k is approximately equal to R 12 k. Then around the seasonal lags, we observe the repetition of the regular part of ACF of both the sides on both the sides of each seasonal lag. For instance, rho 12 k minus 1 is approximately equal to R 12 k R 1 and rho 12 k minus 2 is approximately equal to R 12 k R 2. Rho 12 k plus 1 is approximately equal to R 12 k R 1 and rho 12 k plus 2 is approximately equal to R 12 k R 2. So, you around the seasonal lags, you get some kind of symmetric behavior of ACF. Now, we consider this example. ZT is generated by the process 1 minus b 1 minus b to the power 4 yt equal to 1 minus 0.6 b 1 minus 0.8 b to the power 4 ut. So, definitely you have quarterly data. Then the regular component is MA1 and its ACF is you do not have any autoregressive term here, you have just one MA1 term here. So, its ACF is small r 1 is equal to minus, you have minus sign here 0.6 upon 1 plus 0.6 square. So, finally, you get this value and R j is equal to 0 for all j greater than or equal to 2. Then the seasonal component is also MA14, this part is MA1 and 4 and this one is MA1 and its ACF is R 4 is equal to minus 0.8 upon 1 plus 0.8 square, which is 0.64. So, ultimately you get minus 0.49 and then capital R j is equal to 0 for j not equal to 4. Then you can obtain rho 1 equal to R 1 and then rho j is equal to 0 for j equal to 2 3. Both rho 3 and rho 5 are equal to R 4 R 1 which is 0.2162 and rho 4 is equal to R 4 which is minus 0.49. Then rho j is equal to 0 for all j greater than or equal to 6. So, you observe that these rho j's are 0 in between for j equal to 2 and 3, then again around 4 you have the effect of seasonality. Rho 4 is non-zero and two near points to rho 4, rho 3 and rho 5 are also non-zero. Similarly, you can obtain the partial autocorrelation function also, although the expression for partial autocorrelation function is more complicated. In partial autocorrelation function, PACF of regular structure appears in the first lag, then PACF of the seasonal structure appears in the seasonal lags. At the right of each seasonal coefficient, the PACF of the regular part appears and then the corresponding to positive seasonal coefficient, the regular PACF appears inverted and corresponding to negative coefficients, the PACF appears with its sign. Then to the left of the seasonal coefficient, ACF of the regular part appears. So, here I have plotted the ACF and PACF of some say AR process with seasonality AR12 process, you can say. So, you see that after the lag of 12, the ACF is significant. In between, the ACF is insignificant or 0 actually. We have also shown the PACF of the same process, then these are the ACF of MA12 process and PACF of MA12 process. Then these are the ACF and PACF of AR1 MA12 processes. This behaves like the ACF of AR process. Up to this point, again it starts increasing and then decreases. Similarly, you have PACF of this process. This is the ACF PACF of AR1 AR12 process. Again you get the same kind of picture. After each lag of 12, this again increases, then again decreases and so on. We also observe the symmetric behavior of ACF after 12 months or after 24 months. So, we have discussed the seasonal autoregressive integrated moving average models, and then we observe that this Box-Jenkins approach provides a way out for modeling data which have seasonality. These models also take care of non-stationarity in the data. If the time series becomes stationary after taking few differences, then you can make it stationary first, and then you can also apply seasonal differences. And we have also observed that these seasonal differences take care of all the 3 cases of seasonality which we have discussed in this lecture. For identifying the order of seasonal autoregressive and moving average terms or the usual autoregressive and moving average terms, you can use a ACF plot or PACF plot. So, these models also gave you some idea of how the seasonality is evolving through the past observations. You do not get this kind of idea from the seasonal indices obtained using classical time series approach. So, I am going to stop here. Thank you.
Hi, I am Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debayan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I am interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now, before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with the 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors, like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday. So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits, and as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So, what we did is, for falsification test, we took ear complaints and infectious diseases. Now, ear complaints like if you are deaf since birth, or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age and by weight, we did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a woman's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol and your incidence of getting high cholesterol. Now after this we went in for a policy implication, and in the policy implication we tried to find two policy implications, what matters and exactly how much portion matters. So as far as how much portion matters, we have found that on an average 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices because it has a impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.